this little worksheet was meant to kind of be intuitive, to where, like, read it, just kind of figure things out, think about it, and it's supposed to kind of like lead you into what we're talking about today, to kind of give you a foundation based on what you already know for what we're going to be learning. So I give you this little story here about an average speed of a vehicle or various intervals in the given table below. So this guy's been driving for a while. I guess these are going to be hours, huh? 5 hours. All right, so for the first hour, his average speed is 40 miles per hour. That doesn't mean he's always going 40 miles per hour, right? Speed could be changing, but his average speed is about 40 miles per hour. And then after that, on hours 1 to 3, his average speed was 60. So maybe he got on the freeway or something. And so on and so forth. You guys good? So estimate the distance traveled by the car. Show your work below. So this is where I'll just kind of throw out some bonus points and let you guys tell me what you did and how you did it. Who got number 1 and wants to share what they got?
Orion did 40 times 0.5.
Orion did 40 times 0.5. Why did you do 40 times 0.5?
Because it's speed times time, and so 40 is the speed, and then 0.5 is between 0 and 1. That's the time.
Oh, okay. Okay, then Orion was definitely more. I'm not going to do 0.5, though. What we want to do is how long he was driving that speed. So what are we going to say? 1 hour. So now all that's going to tell me is he went 40 miles for the first hour. So let me get Orion his credit here, and we'll ask Pearl to pick us up from there. Now what, Pearl?
Oh, well, I got 230.
The final answer is 230? And how did you get 230?
So for 60 miles per hour, I did like there's 2 spaces in between.
Okay, so he was driving 60 miles per hour for 2 hours, right? Which is? Good. And then?
For 50, he was doing for 1 hour.
50 for 1 hour. From 3 to 4 is 1 hour.
Yeah. And then 20 was also an hour.
20 was also an hour, which I'm going to squish right here. And then, where do you get 230 from?
70 plus 130 is 190.
Okay, so you just add them all up, right? So there you go. So we added together all of those speeds, right? And we got that. All right. Speed time time. Next one, graph the information. So for this one, I can't really call on you. I'll just kind of tell you what it was. But for the first hour, he was driving 40 miles an hour, right? And then the next one was 2 hours long, wasn't it? And how fast was he going there? So that would look like this. And then what? 50 for an hour? And then? Okay. And it says find the area under the curve. So someone want to chime in on that? Huh? 140? Well, let's see if we can find out how Pearl got 140. So she says 140. So we have, it's probably wrong. Let's see. So we have 40 is the height, right? What's the base? So what's the area of this little rectangle? What is the base of this triangle here, or this rectangle? Times height. These numbers should be looking familiar. 50 times 1. And then 20. Those are the same numbers that Pearl gave us earlier. Remember that? Oh, you drew it like a curve? So like you did this. I don't know. Like this.
From like this, I don't really know how to describe it to you.
Oh, okay.
I don't know why.
Oh, okay. That's interesting. That's interesting. Okay. Fair enough. All right. So the answer for area under the curve is 230, right? All right. Let's keep going on and see what else we can get out of this here. Oops. Conclusion. So what does the area under the curve tell us? What did anybody put there? I'll take that as an answer. I'd have to. The reason why we can't say that's necessarily the case is because we don't know what the curve looks like. So depending on how you draw it, it's hard to say. Also, it's going up and down. So for it to be an underestimate, it either has to be always increasing or always decreasing. Because as soon as it goes up and over, left hand does the opposite, right hand does the opposite, so it changes. But any other thoughts on what the area under the curve tells us? Particularly about the vehicle that we're talking about? Well, the miles traveled. Thank you. Yeah. So it tells us that the distance that the vehicle actually went. Okay. Now, so I want you guys to understand that. This is a graph that represents the what of the car? The average speed, right? Speed over time. So it would seem that if you find the area of a speed graph, it tells you what? The miles driven. Okay? So in calculus, how do we represent area under the curve? What? Integrals. Good. So if you integrate a speed function, I'll call it s of t, over time, that's dt, that means speed times times gives you distance, and you add all those up, what that will give you is the distance traveled, okay? The total change in position, okay? So, let's go ahead and transition into our lesson here, and hopefully that will kind of prep our brains a little bit for what we're learning here. All right, so we're in Unit 7. This is our last chapter of calculus. After this one is done, let's review until your AP. Okay? So these are rough estimates. I think it might go a little over in different places, but kind of being broken up into 3 topics. But basically, Unit 7 is all about how do you use integrals to do things. And so the first one that we're going to look at, that's what we're starting on today, is something we call net change. It tells you how much something is changed over time. Okay? Integrals can be used to tell you how much change is taking place over time. And that's what our warm-up was there. It was like, okay, so if you integrate speed, it tells you the total change in distance. Okay? That's one thing. The second topic we'll get to after that lesson of about 4 or 5 days is over is we're going to look at area between curves. We've done area under the curve, but we haven't done area between 2 curves before. Third thing we'll look at is volumes, how to calculate the volumes of shapes using integrals. So that's our total view there of Unit 7. Let's go ahead and take a look at our objective. By the end of the day, you'll be able to use integrals to determine the amount of change that takes place over a given period, given the rate of change. Okay? So, fancy language, but just saying basically, if you know the speed, you can find the total distance, right? Find the amount of change that takes place over a given period if you know the rate of change, the speed. All right, so let's take a look at the net change theorem. If f prime of x represents the rate of change of quantity f of x, then the definite integral of f prime of x from a to b gives the total change or net change of f of x on the interval. So think of this as speed being multiplied by time, and you add all those up, it tells you the total distance, right? Rate of change times time tells you the total change in your original function, f. Okay? So, I got a few little notes here. So this is my rate of change here is the f prime of x. You might want to draw an arrow to the f prime of x, by the way, on your notes there, because it's not the whole integral, it's just the derivative that represents the rate of change. The interval of time that we're looking at from a to x, a represents the starting time, x represents your final time. So when we're looking at that area under the curve problem we had at the warm-up today, You know, we started off at time equals 0, and we ended at what? Time equals, I forget, 5 or 6? So that represents your total time you're looking at there. Net change. So this represents your final position and your starting position, and if you subtract those, it tells you the total distance, or the total amount of change that has taken place for your derivative function. Now, it's not too uncommon for them to take this number here, the minus f of a, and add it to the other side. If you do that, it looks like this. You guys agree? Okay. So what's kind of neat about this representation is this represents your final amount. This represents your starting amount. And this represents the change that's taken place. So once again, connecting this to our story about the car, right? The car is, first of all, at a position of 0. It's gone 0 miles, right? And then it travels 230 miles. And that'll tell you where the car is located at the end. So you take the start, you add how much has changed, and that tells you where it lands. Okay? All right, so let's go ahead and jump into some examples here. Example 1 says, a chemical flows into a storage tank at a rate of h, which is represented by 180 plus 3t liters per minute, where t is the time in minutes, and this t can be anything between 0 and 60. We want to find the amount of chemical that flows into the tank during the first 20 minutes. So what they're doing is they're telling you how fast the chemical is flowing into the tank, and our job is to figure out how much actually went into the tank. Okay? So first of all, let's go ahead and do a little bit of a setup here. They want to know how long are they letting this flow of water happen. How long are they letting this flow of water happen? 20 minutes. So we're going, and it says for the first 20 minutes, right? So that means we're starting at time equals what? And we're ending at time equals 20. Okay? Now, what goes in here is the rate that they're giving you. So h of t is the rate, actually. So see, it says here at a rate of h, so we're not going to make that a derivative. It's a derivative of something else. So h represents the rate. So let's go ahead and put h of t here. Now, if we integrate little h, we need to find a way to represent big H. So I don't think we really need to do that right now. So let's just leave it at that. But there's your setup. So you have your time that goes here and your rate that goes here. Now we're going to be doing most of our integrals in this chapter all on the graphing calculator. So I'm going to pause my video. I'm going to let you guys come and grab a graphing calculator. Okay, so go ahead and clear your calculator out. Push y equals. What we're going to do is we're going to go ahead and type in the function that they gave us. What was it? It was 180 plus 3t. Okay. We're going to use x instead of t because that's what they gave us. So push y equals and then type in your function 180 plus 3x, or t in this case. Okay, let's go back to the home screen. So push second and quit. Now what we're going to do is we're going to calculate this integral here. We want to calculate the integral of h of t from 0 to 20. So go ahead and push math and 9. And now you guys are going to just type in the integral. Now you guys have nice calculators. If you have an ugly one like mine that says FNINT, you can follow my lead here. But if you have a nice one, just go ahead and type it in. But so the first thing you're going to type in is your function. Now instead of typing 180 plus 3t, I want you guys to start getting into this habit. I want you guys to type in y1. So the way you do that is you push vars, go over to y vars, click 1, and 1. I want you to get in the habit of just having that function stored under y1 and then inserting that, okay? That's going to be very helpful in this whole chapter. All right, next we're going to push. Does anybody have one of these ugly calculators like me? You do? It looks like that. So the next thing you got to do is push comma x, and then comma 0, comma 20. You have to put the x so the calculator knows what variable you're integrating, and then 0 and 20 represent the time limits. And so we should be getting 4,200. Okay, so
What's the comma?
it's like in the middle somewhere.
Oh, right there. For 0, 20, and
Okay, now the units in this chapter are kind of important, you guys. What are the units of, and I would write these notes down here, what are the units of h according to our little word problem here? It's liters, good, liters per minute. Now this here, dt, that represents time. So if you are integrating, what you're doing is you're multiplying this rate by the time factor there. What's liters per minute multiplied by minutes? If it was in the bottom, it would be. But now this is on the top, so they actually cancel each other out. And so you end up with minutes. So, I'm sorry, liters, not minutes, sorry, liters. So what this means is there you go. On the interval from 0 to 20, if you have this chemical flowing into a tank at that rate, after 20 minutes, 4,200 liters would get in there. Okay? Let's go ahead and take a look at part B. If there was initially 500 liters in the tank, how much will there be after 20 minutes? John and Mateo, can you guys both put your cell phones in your pockets and off of your desk, please? So if we start with 500 liters in the tank, how much will there be after 20 minutes? Yeah?
42,000?
No.
Wait, no.
Okay, so according to our answer number 1, how much water flowed into the tank, you guys? 4,200, right? So if it started with having already 500 in there, how much will it have after 20 minutes? 4,700, right? So you have your starting amount was 500, right? Plus the amount of change that took place, and that was 4,200, for a total of 4,700 liters. So that kind of takes us back to that last slide where we said starting amount plus the change that took place tells you the total. Okay? Let's take a look at part C. Write an integral function, h of x. Notice I'm using a capital H there. That represents the amount of chemical in the tank at time t equals x, provided that h of 0 equals 500. So in the problem, you guys, what does 0 represent? Initial time, right? And what does the 500 represent? How many liters there are at that time. So at time t equals 0, there's 500. So that's just a math way of saying what I told you guys up here. There's 500 liters in the tank to begin with, okay? So we want to write an integral function. And the one I'm going to go with is this one over here on the right. I want to set it up like that. So we're going to have h of x is equal to h of 0 plus my integral, right? So this is actually a pretty common question on the AP exam. They're going to want you to write functions. I'm going to do it up here, though, so you guys can see a little bit better. But h of x is equal to the starting amount plus the integral from what to what? 0 to, we've been doing 20, but it's not telling us the final amount for this one. It just says ending at any random time x. So it's from 0 to x, and we are integrating the h of x function, the little h of x function, which I think should be a t, actually. dt. So now this is kind of like a little formula you can use to calculate any answer you want to. We can simplify it, though. What is h of 0 equal? So you'll probably want to just put this. The first one's correct as well, but the second one would be more useful. So there you go. So the final amount of fluid in the tank at any given time is the starting amount plus the amount of change that has taken place on whatever time interval you want. Okay? So the integral tells you how much change has taken place. And if you add that to the starting amount, you get the final amount. Okay? And that's an integral function for net change problems. Let's go ahead and take a look at having you guys try a couple here. So go ahead and try out this slide real quick. They're very popular types of questions. Big time. There's like a whole section in your blue books devoted to net change problems. So we're going to spend a couple days on this. But there you guys go. So number 1 is 154 rabbits. Number 2, you have start plus change equals total. And I want you guys to see that this is the same thing as what I just set up there. Start plus the change, remember the integral represents change, gives you the total. Okay? So there you have it. Let's go ahead and move on to something else. Now, you guys ever notice that whenever you're taking a shower, it never overflows under the floor? That's because somebody was very careful to design that shower in a certain way. They made sure that the rate at which the water is coming out is slower than the rate at which it's leaving. Right? Because if the water was coming in faster than that drain could handle, your shower would overflow, right? So you have water coming in, you have water leaving. That's what we call a rate in, rate out question. Okay? So let's say that I of t tells me the rate at which something's being added, like water coming in from your shower. And O of t represents the rate at which it's leaving your shower, in other words, draining. So rate in, I put I, rate out, I put O, I and O, right? Then the total rate of change is the difference between those. So for instance, let's say water's coming out of your shower at 1 gallon per minute, right? Then the rate out, let's say the rate out is leaving at, 0.5 gallons per minute. Then you're going to overflow, right? Because 1 take away 0.5, you're going to be left with an extra half gallon every minute in your shower because it's not leaving fast enough and eventually it's going to overflow. But you guys saw what I did there. I subtracted it. You take the rate at which it's coming in and you subtract from it the rate at which it's leaving, and that tells you the total rate of change. Okay? So that's what we call a rate in, rate out question. And that's most of what those FRQs are related to in your blue book. So here's your net change then. Net change is what you would get if you integrated these over time, right? Just like when you integrate your rate, it tells you the total change that took place. Well, if you integrate R, that's like you're integrating both of these. So if you want to find the total amount of change that's taken place, you just integrate that function. And then from there, if you're looking for a final amount, notice it's the same exact setup I have here. We have final amount, right? What's this one represent? Initial. And this represents the net change. But notice what's different on this problem from the last slide, other than the fact that I changed the letters, is instead of just having one function in here, I've got two that are being subtracted, a rate in and a rate out, to give a total rate. Does that make sense? So it's the same thing, it's just that we're doing two at once, being subtracted from each other. So let's go ahead and put that to work for us here. Example 2. The rate at which rainwater flows into a drain pipe is modeled by the function R of t, where R of t is that. Notice the unit's cubic feet per hour, so you've got that much water coming in. T is measured in hours. The pipe is partially blocked, allowing for the water to drain out the other end at a rate modeled by this. So here's our rate in. Water's coming in at that rate. Water's leaving at that rate. If there's 30 cubic feet of water in the pipe at T equals 0, that's our starting amount, right? Find how much water is in the pipe at T equals 5. So, first of all, let's set up a function here. Let's set up an integral function real quick. So, they don't tell us a variable for all we know is the rate in and the rate out, but they don't give us a variable for the total. So let's make up our own, and when you're doing an FRQ, if you're going to make up your own letter, you need to define it. So let's say, let T of X represent the total amount of water. At any time T equals X. So T represents how much water we have at any given time T. Okay, so if that's the case, then the total amount of water would be equal to the what? The starting amount, right? Plus the net change, right? From your starting time, which we'll say is 0, to your ending time, which is X. And then in here, we're going to have rate in minus rate out. So what function represents the rate in again? You're right. You're right. I'm not going to write that. I'm just going to put R. But you're right. It's that one. So R of T minus my rate out. What's my rate out? dt. Over time. There it is. So we have our final. We have our start. And we have our total change. And this is the rate in. Oops. This represents the rate in, and this represents the rate out. Okay. So now they want us to find how much water is in there at what time? 5 hours. So what that's going to be then is the following. T of 5 is equal to T of 0 plus the integral from 0 to 5, R of T, D of T. So this is where our calculator is going to come in handy right here. So let's get our calculators out and do some typing here. So the first thing we got to do is I've got to clear my screen, you guys. Let's go ahead and turn on our calculators again and go ahead and go to y equals and clear the functions that you had in there before. We're going to type in the two functions that they give us. So R of T. R of T is going to be 20 sine, and then it's going to be T squared, in this case X squared for us, over 35. Now we're also going to push the down arrow and get into y2 now. We're also going to type in the other function there, the out function. So I just typed in the in function. Let's type in the out function. The out function is negative 0.04 x cubed plus 0.4 x squared plus 0.96 x. So we put our functions in. Now go ahead and push second and quit back to your home screen. Okay, so before we start typing in the integral, guys, what am I going to put in this place? What's t of 0? What's the starting amount? 30 cubic feet of water, right? So we're going to type into our calculator 30 plus that expression right there. Okay? So Andrew, you'll want to follow along with me because we both have the ghetto calculators. The rest of you guys could probably just type it in as you see it there. So here we go. So 30 plus math 9. And we're going to put in y1 minus y2. Now it's important to remember which one was rate in, which one was rate out, right? We typed rate in first, so that's going to be y1 minus rate out, which was y2. So vars, y variables, 1, y1 minus y2. Repeat the same process. Okay. And then comma for me and Andrew here. X, comma, and we're going from what to what? 0 to 5. Oops. And then enter. Okay, so what are we getting for t of 5 then? 30.5. Now give me 3 numbers past the decimal. 30.5, 39. What comes after the 9? 1. So you got to, and just so you guys know, in your FRQs, when you're using calculators, you always round to the thousandths place. Okay? If you don't, then you could lose points actually for that. So now let's get our units right. This is 30 what? That's cubic feet of water. So we'll put feet cubed, right? What about this? What are the units for this? Well, both of these are what? R and D are both what? Those are cubic feet per hour. And we're multiplying that by what? Hours, and therefore it's also just cubic feet. So we're taking cubic feet, we're adding it to cubic feet. So what's my final answer? Cubic feet of water. So there it is. If we have a rain pipe with water that's flowing in at this rate and flowing out at this rate, and it starts with this much water inside, after 5 hours, this is how much you'd have in the pipe. So apparently, the rate in, rate out is pretty comparable. It didn't change, right? We're at 30, and after 5 hours, we only have another half a cubic foot in there. So obviously, they're not too far apart from each other, the rate in and rate out. It's not much change, right? Or maybe it changed over time. Maybe at some points it was flowing in really fast. At some points it flowed out really fast. Who knows? It just depends because it's changing. But there you guys go. So let's throw one at you guys here, and that'll be the end of our day. See how you do with that one.